Hey everyone, in this video we're going to be talking about properties of logarithms. So we will work with the properties. We're going to write log expressions as a sum or difference of logs, and then we'll write a logarithmic expression as a single log, and then we'll also be evaluating some logs whose base is not 10 nor the letter e, the number e. Okay, so these are two properties and we're going to just prove both of them. So you can use these every time you see them, and we'll just prove that they are always true. Okay, so the first one, log base a of 1 is always 0. Okay, so quick reminder, your base for your log is always positive by the definition, and it's never 1. That's just part of the log rules. Okay, so we have the following is always going to equal 0 because what we know if we rewrite this. Okay, so let's say we didn't know the answer was 0. Well, we say that log base a of 1 is something. The something we're calling is y. And then we rewrite it in exponential form. So quick reminder, logs are equal to the exponent on an exponential expression. So if you want to go to exponential form, you say your base a to what the log equals as the power. So whatever's on the other side of the equal sign is the exponent, and then it's going to equal that argument, x. So that's exponential form. You can also always go the other direction if you need to. You can go from exponential form back to log form. Okay, so we just went to exponential form, and now you ask the question, a to what power equals 1? Well, that power has to be 0, because anything to the 0 power is 1 from your laws of exponents. I mean, technically not 0 to the 0, but any other number to the 0 power is 1. And so that means that y must have been 0, and therefore this is our property. Log base a of 1 is always going to be 0. All right, let's go ahead and show the next one, that log base a of a equals 1. So let's say we don't know what it equals, so we set it equal to y, and then we'll go ahead and rewrite it in exponential form. So base a here to the power on the other side of the equal sign, so to the y power, equals this a, so this a here. And then you have to just ask yourself, how would this be true? What does y have to be? Well, for a to stay itself, the exponent must have been 1. That's the only way to keep it the same value, and so y must have been 1. And therefore, log base a of a is 1. So this is always true as well. So if you see something like log base 8 of 8, you know that it's always just going to be 1. And then same thing with our last property we just looked at. If we said something like log base 8 of 1, that answer is always 0, because this says 8 to the 0 power is 1, and this one says 8 to the first power is 8. All right, so there's our two properties. So let's talk about two more properties. So these ones, we have a few assumptions we have to make. M and a are both positive real numbers. A can't be 1, and r is any real number. Okay, so here is the next two properties. That a raised to the power or exponent, that's log base a of m, that's always just going to equal m. And then the other property says log base a of a to the r has to be r. So let me just show you quickly why these are true, and then we'll use these in some examples. So let's start with the second one. This one here says a to the power on the other side of the equal sign, r, equals the argument. And so the argument is a to the r. Well, take a look at that. That's always true. Okay, so that one's pretty nice. The second one here, or let's go back and the first one. This one, if you think of the exponent as y, so we say, okay, a to the y, we're trying to prove real quick that that's really m. And if we know that y was taking the place of log base a of m, well, if we use our rule that says we can rewrite this as an exponential equation, a is the base, y is the exponent, and m is what it equals. And so that's exactly what we already had. Okay, so just proving those two really quick. And now that we know them, we can add them to our list of properties and use them. So let's go ahead and use those properties for the following. Okay, so this one's from our first property we just looked at on the previous slide. The bases match, so 3 to the log base 3 power of pi. We know that that has to be the argument pi. Okay, so that equals pi because of this format and this number right here. So before I write it, what's the next one? The bases match, 7 to the log base 7 power of square root 3 has to be square root 3. And then what about this one? This one, ln of e, do a rewrite on this one. This one's negative 13 because if you rewrite this, this is log base e. Remember, that's ln. Log base e of e to the negative 13. This is our second property that says e to what power equals this e to the negative 13. So it has to be that same value. All right, here's some more properties, lots of properties. So on these ones, we have the product that equals a sum, and then the quotient that equals the difference. So here's how these two work. Okay, so we're gonna just add these to our list of properties. So if you have a log of an argument that's a product, meaning you're multiplying, what you can do is you can take this single log expression of this product and separate it into two log expressions, 1 and 2, if you separate them with a plus sign. Okay, so the first factor, m, goes in the first log, and the second factor, n, goes in the second log. So this can happen every time. If this is a product to start with, you can separate it as the sum of two different logs. You can also go both directions with these properties. So let me erase some of this stuff and just show you really quick that you can do this the other direction. So let's just say that you started with log of base a of m and you were adding it to log of the same base, and then the argument was n. Then you can go this direction and say that it equals a single log where you multiply the two arguments. So these go either direction. Very similar for the next one, the quotient. This one says if I have the log base a of one value or expression on top divided by another expression on bottom, or just one value divided by another one, then I can separate that into two logs. First log, the argument is the numerator, and the second log, the argument is the denominator. And then we separate them with a minus sign. We subtract on this version when it used to be division. Notice on the last one, you add from the multiplication. And also this one goes both directions. If you start with two logs that are getting subtracted, as long as the bases are both the same, you can go backwards here and write them as a single log where you divide the arguments. All right, one more property here that we're going to use, and then we'll look at some examples. So this one is the log of a power equals the product of the power of the logs. All right, so two versions of this. So look at the first one. We have log base a of m to the r. What you can do is you can actually take this exponent on your argument, and you could think of it as like bringing it out to the front. And when you do that, you multiply. So you have that what was an exponent is now going to multiply the log. And these are equal. You can type them in your calculator and see that they're always going to be equal. Again, you can do these in both directions. So if you have a number in front of your log, you can take it and bring it back into the exponent position on your argument if you want to. All right, similarly here we have a to the r equals e to the r ln a. So this one says the following if you rewrite it. So let's see why this makes sense. E to the r log base e of a. So we know that we can do two things. We can take this r and bring it back onto this argument. So that's going to be e to the log base e of a to the r. And then we can use the previous properties we just looked at and notice that the bases match. So e to the log base e, the answer is just the argument, which is a to the r. Okay, so we're going to be writing a logarithmic expression as a sum of logarithms. All right, so notice what we're starting with. Log base A of a product, okay? And we're just told that x is greater than 0 because the argument of your log needs to be positive. So here's the product, and if it helps, put a multiply sign. Okay, that makes it very clear that this is a product. And we have a property that says we can separate this using addition. So as a product, this is our first factor. This is like m from our property. And then this is our second factor. This is n from our property. And so what the property says is that I have two logs now with that base, in this case base A, 1 log, 2 logs, and then each of the arguments, each of the factors of the argument just go into the logs. So there's x squared, there's square root x plus 1. So again, real quick, you're taking 1 log and you're separating it into 2 logs. That's how this property works if you go this direction. So 1 becomes 2. And then you can simplify this one. So that's our sum property. But now let's use our power property. Square root is the same as 1/2 power. Okay, brief reminder from that. From when you learned about exponents, that is going to always be the 1/2 power. And in general, if you have a number here, let's say this is B and this is A, then you can always rewrite radicals with exponents if you say the power was A divided by the index B. Okay, that's always true. So these are just from when you learn about exponents. So that's why square root x plus 1 is the same as x plus 1 to the 1/2 power. So from there, we have a rule that says we can bring the powers down to the front. That was our property we just saw. So this exponent of 2 comes down to the front and we multiply. And this power of 1/2 comes down to the front and we multiply. And so that is the final answer as far as rewriting this expression. And it's pretty much more of like an expanded version. So these are equivalent, the original here and this result here. All right, let's do another one real quick. So we are going to write this expression as a difference of logs. It's going to be a difference because notice the argument has division in it. We have a numerator and a denominator. So we're going to use our difference rule. And so notice that the numerator becomes the argument in the first log, and then we subtract, and the denominator becomes the argument in the second log. So that's using our quotient-to-difference rule. Then we're going to use our power rule that says these exponents can come down to the front with multiplication. Same thing on this one here. And so we multiply. So that's using our power rule. And then that's it. That's as simplified as this one can get. So we went from having 1 log expression with a quotient in the argument to 2 log expressions here. And we have no exponents because we brought them down to the front. Try another one. So we're going to use both sum and difference rules for this one. That's because if you notice, the argument has a quotient. We are dividing the numerator by the denominator, but the denominator has a product. So we're going to use both properties. Okay, so start with the quotient. And so the numerator is the argument in the first log minus the denominator is the argument in the second log. Okay, so that's using our division property or quotient to subtraction. From there, we're going to use the sum property that says if I have 2 factors in my argument, then I can separate those into 2 logs if I add the 2 logs. At the same time, let's go ahead and rewrite so we can start working on exponents. Rewrite this radical here. So this is going to be x squared plus 2. And notice there's an invisible 1 inside the radical on that whole expression. And so the numerator of the power becomes 1 divided by the index over here 3. So a cubed root is just the same thing as a 1/3 power. So now we've used both the sum and difference properties, And let's use our power property in just a moment. We'll just distribute that minus sign. So take this negative, distribute it here and here. And then we'll bring all of the exponents down to the front using our power rule. So 1/3 comes to the front and you multiply. 2 comes to the front here and you multiply. And then this 2 comes to the front as well. And so this single logarithm becomes 3 logarithms in this expression, and these are equivalent. Now we're going to go the opposite direction. So notice what we have. We have log expressions with more than one log in each of these expressions, a, b, and c. And so we're going to write them all as a single logarithm. So we're doing exactly the other direction of what we just tried. So notice that there is a number multiplying in the front of the log, so let's start there. That number we know is going to be an exponent if we bring it back up. So that power can come up here and be the exponent from our power rule. Then notice that you have the sum of 2 logs with the same base. And when that's the case, we can use our product rule that says it's the product of 2 factors when we rewrite them as 2 separate logs with a plus sign in the middle. Okay, so then we can just go ahead and say that that's 5 times 8 as a single log. So this is the part where you condense 2 logs into a single log using your property. So 2 logs become 1 log when we use this property. Just like the opposite happened when we did it the other direction. And so that's log base b of 40. So that's exactly the same as this statement here. These are equivalent. How about this one? Notice the numbers multiplying in the front would be a power, so let's start there. And so that's going to be ln to the 2/3, 27 to the 2/3 power. And then 6 squared, go ahead and just say that that's 36. So we just simplify a little bit. This becomes 27 in this argument, and 27 to the 2/3 is 9. And if you're not sure about that, that's because if you rewrite from your rules of exponents this expression as a radical form, then you can write it like this. The 3 was the index and 2 was the power, and so cube root of 27 is 3 and 3 squared is 9. So that's where 9 came from, just from working with our rules of exponents. And now, because we have 2 logs with the same base, there's an invisible e on both of these, and we're subtracting, we can use our quotient rule that says that 2 logs become 1 log if we divide the arguments. So notice the first argument went in the numerator and the second argument went in the denominator. And then let's just simplify, that's 1/3. So ln of 1/3 is exactly the same as this statement that we started with. And we can actually go one step further. We can re-separate this into the subtraction using our property over here. Because if you notice that ln of 1 is one of the special ones, that's always going to be 0, right? Because we know that ln of 1 is 0, or log base anything of 1 is always 0. And so this is equivalent to negative ln 3. So this whole statement became negative ln 3. All right, let's try one more like this. So we have a lot going on here. We have the same base in all of our logs, so that's good to notice. We are adding these 2, then adding this one, and then subtracting. So we're going to use different properties. So the first 2, we're going to say that these 2 are getting added together, meaning we can use our property that says 2 logs become 1 if we multiply the arguments. So notice that we're multiplying x squared plus 4 times the argument of 4. So that's this part right here. Okay, so that part's done. Then we're adding in over here and subtracting the next 2 logs. And so if we just say now from here, notice we went from having 4 logs, 1, 2, 3, 4, to 3 in the second equation. And so now we're going to go to 2, because if we say this log plus this log, we can add those arguments. Let me get rid of some stuff so we can focus on what's there. So we have 1 log with its argument plus another log with the same base and a different argument. So we're multiplying. So we just multiplied 4 times x squared plus 4 times the x from the second argument. Okay, so look what happened. At this stage we had 3 log expressions, and now we're down to 2 in the next one. All right, so from there, the subtraction is connecting them. So think about what's going to happen. 2 logs become 1, and because we're subtracting, we're going to divide the arguments. So this argument is the numerator, and this argument is the denominator. So we went from having 4 logs to 3 to 2 to 1. So 1 log expression. So here's one more property for us that's equivalent in both directions. If we know that 2 values are equal to start with, then the logs of those values are equal, as long as the base is the same. And the opposite is true. If log base a of m is equal to log base a of n, then those arguments must have been the same. So let's approximate log base 4 of 17, and then we're going to round, and then we're going to use the property. Okay, so this means, if you rewrite it, 4 to what power equals 17, if you write it in an exponential form. So what do we know? We know something around there. We know 4 to the second power is 16, and then 4 to the third power is much larger, but it's 64. So 17 is somewhere in between there, and that's because 16 is less than 17 and 64 is greater than 17. And if we have 4 squared for 16 and 4 cubed for 64, then this is 4 to something between 2 and 3. So something here is between 2 and 3. Okay, so 4 to what power is 17? So what we can do is we can take the log of both sides. Now, we're going to apply ln, which is log base e, from the property we just looked at. If this is like m equals to n. If 2 values are the same, then the logs of them are also equal. Okay, so let me just clarify something really quick before we move forward. We are taking the log of both sides, so we are applying log. And you can choose any base you want, and we chose base e. So I'm going to just say log base x. In this case, we pick base e because it's ln. You can pick base 10, base 4, whatever you want. You can pick any base, but we just picked base e. Then what does this tell us? Because we applied log to both sides of this equation, we pretty much took ln right here and ln right here, we applied log to both sides. The whole point of doing that is to go from here to here. The reason why you want to apply logs to an equation is so that you can solve for the exponent. That is the only way that we've been able to bring exponents down. That's the beauty of logs. That's why we learn them, because they are a tool for solving for exponents. So if you think about it, you haven't really been able to bring exponents down out of the exponent position before you learned about logarithms. So by applying ln and then going into this very next step where you bring the power down, this is really, really nice because now y can be solved for. One more step, just divide both sides by ln 4. And y, the exponent, is by itself. So you solve for the exponent. And if you want to use a calculator, that's about 2.0437. And hopefully that number makes a little sense, that it's way closer to 2 than it is to 3, because 4 squared was 16, which was really, really close to 17. And so the power was really close to 2. Okay, so the idea here is that you can apply logs to both sides of your equation, and then one of the main reasons that you would do something like that is so you can bring the exponent down from the exponent position. All right, the last thing to talk about is a change of base formula. And so the change of base formula allows you to pick a new base and make an equivalent statement. So let's say I had log base a, my base is a, of m. I can pick a new base, I'm going to call it b, and these are equivalent. If I just say my new base b, if I divide log base b of m divided by log base b of a, the original base. And so why we care for this is because our calculators, most calculators, the base is 10 or e. On a calculator, the button for base e is the ln button, and the button for base 10 is just the log button. And so if you're asked to find like log of something other than e or 10, then if you want to use a calculator, you have to change it to base e to use this button, or base 10 to use this button. And so remember, it's invisible if it's base 10, we just don't write that, it's just the word log, and it's ln if it's base e. Alright, so let's go ahead and work this out using a calculator. So most calculators, we don't have the option of typing in base 7. So what we can do is we can pick either base 10 or base e. We're going to pick base 10. So our new base is 10, log base 10. And using our change of base formula, the argument goes in the numerator and the base goes in the denominator. So you would just type into your calculator log 52 divided by log 7, and that would be what your answer. It's about 2.0305. Okay, or you can use natural log. You could say base e, you're going to get the same answer. Doesn't really matter. So you could choose base 10 or base e, you will get the same exact answer. Alright, from the next one, let's pick a new base. Let's pick base 10. And so notice the argument went into the numerator, the base went into the denominator, and then you can just type this in your calculator. And so in the calculator, you would just type log button, square root button. It probably looks something like this. And then, depending on the order of the way your calculator works, then 7. And then you would divide that by log square root 3. And same thing, option, you can use the ln button. You can switch this to base e and use those two buttons, and you'll get the same answer. Okay, so that's it for this one, properties of logarithms. Thanks for watching.